Hey there, and welcome back to Unity Netgame Chat, an awesome collection of the most advanced networking solutions built in Unity. Now, ever since the release and success of Fortnite, pretty much everybody has thought that when it comes to building networked games using public game engines, Unreal Engine sets the standard. But with Unity's latest new features and tools that are not only more versatile than those of Unreal, but in my opinion actually more powerful, Unity pretty much sets a new standard for building networked games. Now, to celebrate and demonstrate this, I'm building a new demo that will look to replicate the most advanced features from Fortnite. I'm calling this Unity Fort. Now, I'm actually building this using a custom built networking engine that I've been working on for quite some time in Unity. Now, this engine provides some rather advanced networking techniques that extremely reduce lag, create super smooth player movement, and overall allow for building an extremely stable networked game. Some of these techniques are a lot more advanced than what we see from typical networking solutions such as Fortnite and Mirror. Now, you can download this demo and see these features in action for yourself using the $30 membership on my Patreon page. This obviously as well helps me continue building these demos and definitely goes a long way in supporting my content. In this particular video though, we'll focus on one particular beauty of the functionality within this demo, and that's the ultra smooth player interpolation. Now, all network games have interpolation implemented in one way or another. What we have here is the server on the right and a client on the left. The server is moving this cube in a circular path using some pretty simple functionality. By taking into account a center point and a distance from that center point, the cube is being moved in a circular path using the cos and sine functions of the math library. The part that I want you to pay particular attention to is this part right here. With this code, this means that this particular functionality will only occur on the server. The client can only replicate this functionality using periodic updates that come in from the server. As you can see though, at the moment, the cube is simply in one location on the client. Let's go ahead and add some simple update functionality to make sure that this cube can update every single time the server sends in an update. This deserialized function will run on the client. The serialized function below it will run on the server. Taking a look at the serialized function, we see that we pack the position of the cube into a struct that at the moment I'm calling transform data. Once we pack it into this struct, we then serialize the struct. When the struct is serialized, it can be sent over the network. The deserialized function just above it is called on the client whenever an update comes in from the server. You can see that after we deserialize the message from the server, we then save the position onto our game object. Let's take a look at how this looks in the Unity editor. Once again, we've got the server on the right and the client on the left, and already you can begin to see some interesting problems. The movement on the server on the right is really smooth. On the client though, we have some jitterish movement. This is in a network environment with absolutely no drop or latency. But if I use Clumsy, what I can do is very quickly simulate a drop of 20% in each packet that is being sent over the network. You can see the difference that this makes on the client. It's actually very significant. The question is, why is this happening? Of course, if some packets are being dropped, we would expect to see jitterish movement. But an even bigger reason lies in the very nature of the network itself. Let's go ahead and expand the client scene view and take a look at some debug information that's being shown. At the top here, we have some information that might be difficult to see. But this is technically how often the client is receiving updates from the server every second. You can see that the client is only receiving updates from the server about 5 times a second. What this means is that the client can never really smoothly replicate the movement from the server if it decides to only update its cube every single time an update comes in from the server. To fix this, we need to make use of a previously unused function within our interpolated transform class. This interpolate function is called every frame on the client, and it is also given an extra parameter of the interpolation time, which is a single integer number that represents what frame it's actually being called on the client. What we're doing now in our deserialized function is, instead of updating our transform the moment the information comes in, instead we simply deserialize it and keep it in this cache variable. We then increase a variable that is being used to keep track of how many updates have been received from the server. Inside the interpolation function, we then check if we've received more than 0 updates from the server, and then we set our position to a linear interpolation between our current position and the last position we received from the server. In the Unity editor, we can see some changes that this provides to the network code. The first huge change that should be realized is the fact that the movement on the client is now a lot smoother than before. What you can see though is actually a very interesting phenomenon, that the client movement does not completely represent what movement is being sent from the server. If you look closely, you notice that the cube on the client actually follows a different path from that on the server. This is not necessarily an uncommon situation in network games. For instance, if I was to stop the cube on the server in one particular position, you can see that the cube on the client would soon come to rest in exactly the same position as the one on the server. This kind of behavior is actually expected from network functionality and is usually accounted for in different ways. But this difference is actually too high. And the main thing that I'd like to point out here is how the movement on the client is not 100% smooth. It does have certain periods of time when it appears to slow down, as though there's a certain delay between when it receives updates from the server. This is where our buffered state linear interpolation comes in. To implement buffered state, we'll start by making a change to our transform data struct over here. You can see we've added a new interpolate function that uses a vector3.lab method to interpolate between two transforms, one being a first transform and the second being the last transform. It does this with a final float parameter t, which represents the amount of interpolation that will be done between these two elements. Inside our transform interpolated component class, which is a class that is actually attached to the game object we're interpolating, we then add a tick state sparse buffer. This will store objects of type transform data. This type of buffer is simply a modified list. It takes in a size which will represent how many objects it can store. And every single time an object is added, if the buffer is already full, the last object is then kicked off to give us a pair of states from which we can then derive an interpolation between the two at any given time between the two. What you should see now is that our deserialized function, instead of saving whatever it has deserialized to a variable, now adds a new state to our buffer that we've just created. Again, if the buffer is already full, it kicks the last item off the list and then adds our new item. The interpolate function is now much more detailed than before. At the beginning, we create a new state. This is going to be the result of our interpolated state. And at the bottom here, you can see that we then set our transform.position equal to that state's position. What happens in between is the more interesting part. We just make sure that we have more than 0 states saved from our deserialized function. After that, we create 3 variables, one being the low index and then the high index and a float for the interpolate value. We then use our state buffer to give us all this information. We already have the interpolation time that has been passed in as a parameter. We give this to our state, and our state returns us the low index to use, the high index to use, and what interpolation value to use. Now, this also returns a boolean which tells us whether our state is actually valid according to the different states we have received from the server. What we do here is we export these two states into separate variables. We then pass these two variables into the state.interpolate function that we talked about earlier. Using these two states and an interpolated value that are all provided by our state buffer, the transform struct then exports an interpolated value that we take advantage of. Now, just in case we did not have any valid interpolation, assuming perhaps the server has not yet sent an update, we would just use the last item, which we can helpfully get from our state buffer. Now, once we have the interpolated value or the last value, depending on what it is that we have, we can then go ahead and set our transform.position equal to this state. Back inside of Unity, once again, we have the server on the right and the client on the left. We can see that this allows us to replicate the movement really well. We no longer have issues with the cube not following the exact path that's on the server. Its path is now a lot more accurate. And you can see it actually moves linearly between two positions that are received from the server. Again, remember, this is very extreme conditions because the server is only sending 5 updates per second. In a much more advanced network situation, such as we have with the Unity 4 demo, I was actually sending 20 updates per second. Again, 5 updates per second is actually not a bad test because sometimes you can have network drop off. But as you can see, even in those extreme situations, we can get very smooth interpolation. Thanks a lot for watching this video, and I do hope to catch you in the next video. Make sure to like and subscribe if you actually like this content, and be sure to check out the Discord linked in the description. Catch you soon.